Hello folks, and welcome to the very last review session for Calculus 3208 for your final exam, presented by CDLI, as are all the others. And today we're talking about the last topic of the course, which is logarithmic differentiation. We've already sort of set this topic up quite well, I believe. But today what we're going to do is we're actually going to get right down to the nuts and bolts of doing this stuff to find the derivatives of some functions that wouldn't be impossible, but would be quite difficult otherwise. So let's get rolling right along with this. Alrighty, so logarithmic differentiation. We're going to use log differentiation to find derivatives of functions of this form. So whenever I have a function that has variables in the base and variables in the exponent, so it's a hybrid of a power function and an exponential, then I need logarithmic differentiation to find the derivative. All the other ones that we're going to look at are functions where we don't really need log differentiation to get to the derivative, but it certainly makes our lives a lot easier because they help us simplify complicated derivatives. So let's get rolling. First example, use logarithmic differentiation to find dy over dx. This is an example where I have a function in terms of x in the base and one in the exponent. So I have no choice. I'm going to have to use logs here. So we usually use the natural log. It's the easiest one. Why not? So I'm going to apply that to both sides of my equation as always. Same way we set this up before. And then I'm going to float this exponent down in front. So I have the ln of y equals cosine x times the ln of x. Then I differentiate. The derivative of ln y is 1 over y times dy over dx. So implicit differentiation there. And on the right-hand side, I have a product rule. So the derivative of cosine is negative sine multiplied by ln x plus the derivative of ln x, which is 1 over x, times cosine x. Okay, so can I simplify any of this? Well, not a whole lot, but let's get started on it anyway. So I've got 1 over y dy over dx is going to be equal to cosine of x, and I'm going to get a common denominator here right away. Call it x sine x ln x, and put that all over x like that. So we have our common denominator. So all that remains now to get dy over dx is to multiply both sides by y. And so I have dy over dx equals y outside of that big fraction we just created. That looks like this. And then we got to remember what y was equal to. That's where we started. So that is x to the power of cosine x. And that's multiplied by cosine of x minus sine x ln x. Oh, I forgot an x, didn't I? X sine x ln x. Excuse me. All over x there as well. And I think I'm going to do one more thing here, realizing that this denominator is to the power of 1. Then I can combine it with this expression up here and down here and just subtract my exponents. So my derivative in the end then becomes x to the power of cosine of x minus 1. And that's multiplied by cosine of x minus x, don't forget the x, sine x ln x. And there we have it. Okay, so logarithmic differentiation when we have to use it because I have a function in the exponent as well as one in the base. Most of the rest of the time when we use log differentiation, it's because we have something complicated and we want to make it simpler. So let's look at this one for instance. Here what we have is y equals secant squared over tan x all square rooted. Now we could use a chain rule with the square root from the outside and then quotient rule with the secant squared over tan and then another chain rule with the square and the secant, but that's going to get really gross. So as opposed to doing that, what I'm going to do is I'm going to apply logarithms to both sides and go with this logarithmic differentiation. So very quickly, I know I'm going to start applying my log rules right away here. So this is all to the power of 1/2. So I'm going to float that out in front before we get too far into this. So it's going to be ln of secant squared x over tan x. And then I can split those two up using my log rules because the logarithm of a quotient is the difference between the logarithms. So this is the ln of y equals, and I guess I can leave the half factored out, or I can put it on both of them. I think I'll leave it on both because it's less brackets and confusion. So it's ln of secant squared x minus 1/2 of the ln of tanx, or tan x. Oh, you're welcome. Oh, okay, so there's tan x. All right. So now what I'm going to do is one more step to simplify before I even begin to differentiate here. Secant squared, I can take that exponent and multiply it in front, and 2 times 1/2 goes away. So I just have the ln of secant x minus 1/2 the ln of tan x. And now I differentiate. So 1 over y, dy over dx. It's always the same on the left side, implicit derivative. And then I've got 1 over secant x. Remember, the derivative of a lot of stuff is 1 over the stuff times the derivative of the stuff. And the derivative of secant is secant tan. And I'm going to subtract 1/2 of the derivative of tan x. And if I recall correctly, the derivative of tan is secant squared. So this is 1 over tan times secant squared. Okay, so let's see if we can put all that together in a little more simplified form now. So I'm going to keep dy over dx by itself, and I'm going to multiply by that y. And at the same time, I'm going to try and make this a little bit nicer over here. So I'm going to get out my cancellation pen, my red one, and I'm going to say secant x goes away. And that's all I'm going to make go away here. But I'm going to get a common denominator for both expressions, that being this expression here, and this one over here. It looks like 2 tan x will end up being my common denominator. So when I do that, let's see what we get. We're going to have tan x times 2 tan x will be 2 tan squared. So I'm going to have 2 tan squared x. And then it's just going to be in the other one minus secant squared. And that's all going to be over 2 tan x. Okay, so I got a common denominator by multiplying this one by 2 tan x. And since I'm multiplying this y out of here, I'm going to multiply all that by the original function, which was the square root of secant squared x over tan x. And I guess we can combine that into one fraction. It's not really a whole lot simpler, but I'm going to leave it as the square root, oh, wait a minute, the square root of secant squared is just secant. So I'm going to get rid of that square root, actually. Let's have that one for breakfast. He's gone. So we're going to say the square root of secant squared is just secant x. So up in the numerator, I'm going to have a secant x outside of 2 tan squared minus secant squared. And then in the denominator, I'm going to have square root tan is tan to the power of 1/2. And so the 2 stays there, but I got to add 1/2 to a 1, so I get 3 over 2. So this is the square root of tan cubed x. And you say, that's simpler than doing it the other way? Trust me, it is. Okay, let's roll on. Example 3 coming at you now. So for example 3, what we have to do here is we have to apply another logarithmic differentiation. I'm hoping we're getting to the point now. We're applying that natural log to both sides, and using those log rules comes almost second nature. So let's see if we can do this all in one foul swoop here. So I know that I'm going to end up floating down an exponent of 1/3. So I got 1/3 in front, and I'm going to have a ln of x to the power of 5 minus 2. And then I'm going to be subtracting another 1/3 ln of x to the power of 4 plus 1. And so that's ready to differentiate now. So that made that a little bit quicker and easier there. So let's differentiate ln y. So 1 over y times dy over dx there. And that's going to equal, on the other side, 1/3 times 1 over x to the power of 5 minus 2 multiplied by the derivative of x to the power of 5, which is 5x to the power of 4. And then we subtract 1/3 of 1 over x to the power of 4 plus 1 times the derivative of x to the power of 4 plus 1, which is 4x cubed. Okay, so I'll leave the 1 over y here for now. So 1 over y times dy over dx is going to be 5x to the power of 4 over 3 outside of x to the power of 5 minus 2 minus 4x cubed all over 3 outside of x to the power of 4 plus 1. Now, we should get a common denominator and try and simplify, but there comes a point when you say you got to be reasonable in terms of what's an obvious simplification and what isn't. I don't think that is. So we're going to leave that as it is. We are, however, going to multiply both sides by y, which is, of course, this stuff. So dy over dx is going to be equal to y times everything that we have over here. So it's the cube root of a whole pile of junk here. And our pile of junk starts with x to the power of 5 minus 2 over x to the power of 4 plus 1. And then I'm just multiplying by the two fractions, 5x to the power of 4 divided by 3 outside of x to the power of 5 minus 2 minus 4x cubed over 3 outside of x to the power of 4 plus 1. Yippee skippy. Got it. Logarithmic differentiation. We're rolling right along. One more example. Okay. So use logarithmic differentiation to find dy over dx for this one. All right. Ln y is going to be equal to. This one looks like it's going to be fun. So I'm going to split this into 3 logarithms, all of which we've got a big square root exponent, so it's going to be a half times all of them. So I've got ln of x squared and 1 plus ln of x squared minus 3 and plus ln of x squared and 2. Alrighty, so then what we're going to do is we're going to differentiate. So this is 1 over y, dy over dx, and that will be equal to here. So it's 1/2 of 1 over x squared plus 1 times 2x. Okay, that's going to be nice. Plus 1/2, oh, this whole thing is going to be nice, over x squared minus 3 times 2x plus 1/2, yay, of 1 over x squared plus 2 times 2x. Okay, so that's all well and good. And we're going to grab the red pen here. Look out, we're going to be canceling. So we'll grab the cancellation pen, and we got a 1/2 and a 2 and a 1/2 and a 2 and a 1/2 and a 2. So now what we'll do is we'll write all of that more concisely as, let's see what we got now. Dy over dx, I'm going to multiply by y in this step too. And we're going to have x over x squared and 1 plus x over x squared minus 3 plus x over x squared and 2. And all of that has to get multiplied by the y that we had over here. And y was the original disgusting thing. So all of that is multiplied by the square root of, yipes, x squared plus 1, x squared minus 3, and x squared plus 2. And so there we have it. Differentiate it using logarithmic differentiation. Could probably be simplified more, but I'm doubting very seriously it'd be worth the effort. All right. Let's see. The your turn question. Okay, the very last your turn question in all of these review videos. Sad? Nah, it's all right. We're good here. Okay, hope you're all right too. So use logarithmic differentiation to find dy over dx for both of those functions. So if you want to pause the video, go for it. Work it out. I'm going to jump to right here, which is the solutions for both of those. So worked out in all of their gory details. Fun, fun, fun. Doesn't get any funner. And from there, we're just going to summarize some of the things that we talked about in this particular session. So some of the key ideas we had here were, we use logarithmic differentiation to differentiate functions that have a variable in the base and the exponent. So stuff like y equals x to the power of x, or more generally, as we saw here today in the session, y equals f of x to the power of g of x. So one function up top, one function down the bottom makes a mess, so we've got to use logs. To simplify the differentiation process, we can also use logarithmic differentiation. We have a relatively complicated function, which would imply multiple uses of product quotient chain rules, of course. The basic idea is to apply the log to both sides, simplify the equation, and use your laws of logarithms to break it apart, in other words, and make it easier to differentiate. But as always, it is important to be very careful with your product, quotient, and chain rules when differentiating more complicated expressions. But the good thing about log differentiation is it eliminates most of the headaches that come along with that stuff. So in that regard, certainly makes your lives a lot easier. I really hope these videos have been helpful to some of you, and I hope you're going to do well on your final exam. Don't hesitate to ask questions. That's what we're here for. And all the best in the future. Good luck.